Good morning, everyone. Thank you so much for joining today's webinar session. My name is Adebola, and I'm the Business Development Lead at Accrete. Welcome to today's webinar as part of our webinar series. Today's webinar is titled Integrated Asset Modeling, Key Considerations and Deliverables. But before we proceed, I would like to take you through an overview of our company and our services. Accrete Petroleum Limited is a fully owned Nigerian consultancy firm specializing in the offering of field management solutions within the upstream oil and gas industry. We have partnered with globally acclaimed OEMs in the sale and deployment of field management softwares, the integrated production modeling software, and the digital oil field suites, both by Petroleum Experts and the Axis Hydrocarbon Accounting System by Adept Solutions. We offer consultancy in the use of these softwares through the wireless data gathering system for real-time data, the integrated asset modeling for production optimization, the digital oil field deployment, and other G&G services. We offer trainings on our softwares as well, the integrated production modeling and the Axis Hydrocarbon Accounting related courses, petroleum engineering courses, and the petroleum business courses. Today's presentation will be anchored by one of our very seasoned member of staff in Accrete, Lukman Lawal. Is a senior petroleum engineer with extensive experience within the offshore and onshore oil and gas industry. His specialization covers digital oil field solutions, integrated asset modeling, production technology, and production optimization. He has delivered many projects in the area of field development planning, digital oil fields implementation, integrated asset modeling, and production optimization using cutting-edge field management tools. Lukman is also a skilled trainer and has delivered numerous intensive courses in integrated production modeling, utilizing the Petroleum Expert tools. His expertise, experience, and dedication make him an invaluable asset to any organization looking to optimize their production and streamline their operations. Before we go into the presentation, I'd just like to lay a few of the ground rules. If you have any question in the course of the presentation, please write your question within the question and answer section, and our presenter will do well to respond to you. If you have a question at the end of the presentation, please indicate by using the raise hand signal, and your mic will be unmuted for you to ask your questions at the end of the presentation. In the course of the presentation, we'll be throwing out polls, which consists of questions relating to the topic today. Please do well to answer as we use it to track your engagement. Thank you as Lukman takes the floor.
All right. Thank you, Adebola. Good morning, everyone. And thank you for taking the time to join us on this webinar today. So I'll be talking about integrated asset modeling and giving just some of our experience in delivering projects and using these tools over the years. Some of the key considerations when deploying this kind of projects, right? So in terms of the outline, so I'll briefly go through the introduction, then an overview of what integrated asset modeling is about. Then we talk about the key considerations and typical deliverables that you can get from IAM projects. So these deliverables, I'll be presenting them in form of case studies because most of the deliverables we'll be discussing are from actual projects that either we have done locally or one of the projects that Petroleum Experts have done. So Adebola went through our services earlier in terms of software consultancy and training. And as everyone that's joining may be aware, IPM suits is the global standard for carrying out integrated production system modeling, and is used by more than 500 companies globally. In terms of the integrated asset modeling, for over 12 years now, we've been having we've been supporting clients with the usage of the PETEX IPM suits, which is pretty much the standard for carrying out integrated asset modeling studies. So we also carry out IAM studies for clients, help clients with quality check and quality assurance of their integrated asset models, on-site technical support services, and we hold workshops either to review existing models or to train clients on how to actually build models that can be used to answer problems. So the rationale behind this webinar is that, in many cases, clients struggle to meet objectives, and most of this struggle actually comes from the models not being properly set up. So we'll just highlight a few, major considerations in building your models that would allow you to be able to meet those objectives. So in terms of integrated asset modeling, what it's about for people that are not familiar with the concept. So it's the IAM is pretty much a model that integrates all the components of your production system, from the reservoirs to the wells to the surface gathering network on the same platform, right? And the idea behind having all your models on the same platform is so that you can replicate the performance of the system as it is in reality, right? So if we're able to build a model to replicate the performance of our system, then we can use that model for surveillance, we can use it for planning, we can use it for designs, we can use it to get more from the system, right? Add value to our operations. So what you find that, traditionally in the industry, you'd find these different parts of the production system, the reservoirs, the wells, being modeled in isolation. And once you do that, the problem with that is that, in reality, these systems are integrated, right? And there is dynamic communication between the different components of the system. So when you model them in isolation without integrating them for achieving certain objectives, you end up where you have to make assumptions about the boundary conditions between the different components, right? So if I need to solve my reservoir model and generate forecast over time, then I need to make certain assumptions. If I don't have lift curves, I need to fix flowing bottom hole pressures and generate rates over time. If I have lift curves, then I will need to make assumptions about flowing wellhead pressures, right? But what we know that in reality, these pressures are dynamic in nature. As you produce over time and the reservoir declines, the energy in the reservoir declines, then these pressures will change dynamically as well. As you bring in more wells or take some wells on artificial lift and all that, the back pressure they will have on other wells will change dynamically. And this will affect the performance over time. So the only way to capture this is by integrating the different models as they are in reality, right? So integrating the different models, allows you to capture these dynamics that exist in the actual system, right? And once you're able to capture these dynamics of the system, then you have a more representative model that you can use to make to achieve whatever objectives that you're trying to, right? And also it means that the assumptions that we make across board will be consistent from the reservoir all the way to the surface, right? So capture the system dynamics by eliminating artificial boundary conditions, and also make consistent assumptions across board is why we build the integrated asset models. So in terms of, before we continue, we would have a question, more or less like a poll that would ask, so we'll post a poll and pretty much ask you to type in your answers, just so that we have an idea of what people think of objectives, what kind of objectives people think they can achieve with integrated asset modeling. So the poll will come up now. Once you see it on your screen, just type your answers. So the question is, type in two answers, two objectives that you can achieve with an integrated asset model, or an integrated production model, or an integrated production system model. They all refer to the same thing. So just type in your answers and click on submit. So we'll give you a minute to do that. So once you do that, then we can view your results and share. So I've seen surveillance and optimization. Yeah, that's right. So production optimization. So surveillance, real-time surveillance and optimization, asset monitoring. So type in your responses, then reservoir surveillance, okay. Integrating different disciplines, complete seamless management, reliable forecast. Exactly. So these are pretty much the kind of objectives that you can achieve with an integrated asset model. So what we can see here is that production optimization is very popular, and that's why you see that it's highlighted, right? Production optimization, production surveillance, production forecasting, cost management, reservoir surveillance, asset monitoring. All these are the kind of objectives that you can achieve with an integrated asset model. So thank you everyone for posting your answers, and it shows that we pretty much are all on the same page in terms of what we understand that an integrated asset model can achieve. And most of our the deliverables that we'll be discussing are centered around these objectives, right? Which are production optimization, surveillance, forecasting, and all that. So in terms of an integrated asset model, typically you need a model for capturing the performance of your reservoir, integrated with a model for capturing the performance of your wells, and a model for capturing the performance of the surface network. So once you have that, then all those objectives that we just listed can be achieved with the integrated asset modeling method, right? So these are just also, this slide just shows a summary of some of those objectives that we just listed, right? Optimization, surveillance, forecasting, maintenance planning, part of field development planning and design and all that. So in terms of the key considerations when carrying out an integrated asset model project, IAM, IPM, or IPSM project. So the very first consideration, there has to be some good amount of time spent planning the project, right? So and once you spend a good amount of time to conceptualize the project in terms of what objectives are you trying to achieve, right? So we're not just building models for the sake of modeling, we're building it to answer a question. So the question you're trying to answer has to be properly outlined, properly formulated and understood, right? Then the question you're trying to answer determines what components of your production system need to be part of the model, right? And once you determine these components that need to be part of your model, then that determines what technologies that you need to model them. So we're not just going to build complex models, to answer simple questions. If this question is simple enough to use, say, material balance for the reservoir modeling, then we won't spend months building a numerical simulation model. So that's where the objectives, components, and technologies come in, right? Then the execution itself, once you have this planning, properly worked out, then the execution becomes easier. And the execution, that's where the construction of the model and the using the model to answer the objectives, then the maintenance of the model going forward comes into play, right? So this planning phase is hugely important because typically you're building an integrated asset model. It requires a lot of data and it requires several disciplines coordinating their efforts to achieve whatever objectives that you have. So, it requires you to, spend a bit of time putting all that, synchronizing all these efforts, discipline, and data to ensure that you have a successful project, right? And in terms of, what we need to be part of the model, so depending on the objectives that we're trying to achieve, then we can decide that, okay, what do we have in our production system? Obviously reservoirs, wells, and the gathering system are, for an oil production system, for instance, are fundamental. So do we need to include liquid processing? Do we need to build the model up to the export point? So if we have gas reservoirs, so do we need to include them in the model? Then, also model how much of whatever condensate we get from the gas system goes into the liquid system, the gas exports. Is there any water injection happening? Is it produced water we are injecting? Do we need to build the water injection network and integrate it with the production system? So once you have this, outside of any software at all, you have this, clearly conceptualized, then it makes the task going forward easier in terms of building a model that would appropriately replicate the performance of your system, right? Then once you set out, the components of the system that you need to include, then we start thinking of what software or what technology do we need to accurately replicate the performance of the model. At the reservoir level, do we need a numerical simulation model or a material balance model will be adequate? At the well level, we have a well modeling system. At the surface level, we have GAP. Do we need to now do a detailed modeling of the process system by using a process simulator and integrating it with our GAP model? So it's at this planning phase based on the objectives that we need to answer, that we make all these decisions. And once you make all these decisions, it reduces the number of iterations that you have to do, right? So the objective is clear, the path to achieve that objective is clear, and the tools required to achieve the objectives are also clear. And once that is done, then the actual implementation, can begin. So when we carry out, integrated asset model or IPM project, we also follow a similar reasoning, planning, and workflow. And what you find out is that in any modeling effort, right, what you're trying to model is the fluid flowing from a reservoir through a series of facilities to where you need it. So, and that means that accurately capturing the properties of this fluid, whether it's oil or gas, is critical, right? So the modeling, the property PVT modeling, accurately capturing the properties of the fluid is fundamental to the rest of your effort in the IEM model. So when we have this kind of project, we typically spend the first couple of weeks ensuring that we get representative PVT models, scouring all the databases and ensuring that we capture the required data for modeling the fluid and build the appropriate models. So we'll see PVT modeling shortly, the methods available and how we go about it. Then once the PVT models, are built and the files are saved, then we can move into the reservoir modeling, then well modeling, and now bringing them into the network model before we can now use the models to carry out and achieve our objectives, right? So in terms of considerations, this kind of workflow ensures that you build the model, in a manner that almost guarantees that you're able to achieve your objectives, and also it reduces the number of back and forth iterations that you need to get the objective, achieve your objectives. And it's a similar workflow that we adopt as well when we are, building models. So since the PVT is so important, let's look at the options available for, the fluid modeling, right? So in terms of PVT modeling, like we said, it's crucial to achieving an accurate model, be it reservoir models or well models. PVT is central. So we spend a good amount of time ensuring that we get an accurate representation. And again, we use the appropriate technology. So we do not believe in using a sledgehammer to kill an ant. So we try to if black oil modeling is appropriate to achieve an objective, then we don't spend weeks building equation of state models, right? If we're in a situation where equation of state models are the method, the accurate method, then we won't use black oil model, right? So the methods available are your black oil and equation of state. And those familiar with these concepts know that the black oil modeling is a two-component description of your fluid, and equation of state is a multi-component description of your fluid. And they have their applications, and they have where you can specific cases where black oil is adequate and where condensate is required. If you have near critical fluid, for instance, where there's a lot of phase change and you have liquid dropping out of gas like volatile oil and retrograde condensate, then by all means, an equation of state model is appropriate for that situation, right? But if I'm dealing with just standard black oil, then spending a lot of time building an equation of state model and tuning it to experimental data will not give me any additional edge on the accuracy than using the black oil model. right? So at the conceptualization stage, the planning phase is where we determine, the appropriate technology to use for the particular, type of objective or fluid or system that we have, right? So in terms of, black oil modeling, in IPM, Prosper and MBAL, the recommended workflow is, if you have just very limited data, let's say you have just the GOR of the fluid, API, and gas gravity, then the recommendation is, okay, there's no data to tune the correlation, then you need to now fall back on your experience of the reservoir or field that you're working in the cases where you had the PVT report, which correlation consistently replicates the performance of the fluids. Then you can use that correlation until you have more information available later, right? Then if you have some lab measurements available, then you can use that lab measurement to tune the PVT report, right? So in MBAL and Prosper, we recommend that you use data that has come out from a flash experiment, right? So always use data that has come out of a flash experiment for matching. So that is, if you use MBAL and Prosper enough, you will see that it's emphasized a lot in the user guides. And if you've attended any of our IPM trainings, you also see that we also try to emphasize that it should be data from a flash experiment. So that, the data from a flash experiment ensures that mass balance is achieved. There's mass balance in the calculations, and also the assumption that the process within a well, a flowing well, is closely matched more by a flash process than a differential liberation process. So in terms of the data you need for matching your PVT in IPM, Prosper, and MBAL, so the options available for your match data, if you have separator flash experiments, or I just said differential liberation experiments, or you have an equation of state model of the fluid, then you can generate a match data, a black oil match table that you can now use in Prosper or MBAL to match your PVT data, right? So these are the three options that you can use. A separator flash experiment gives you a single point to match to, whereas the adjusted differential liberation data gives you a series of points to match to. Then if you have an equation of state model built in PVTP, for instance, you can also use it as your match data, right? So these are the three options available for matching your data. So you see that we're spending quite a bit of time on PVT as a key consideration for your IAM because it's critical, to the success of your project. And if you're using black oil method, then these are the options available for you to do that. And these are also the options that we use when we carry out these projects for clients. And then again, to emphasize, these are screenshots from the Prosper and MBAL user guides, and you can see that data from a flash experiment rather than a differential liberation experiment is recommended. And like I showed in the previous screen, these are the options available. If you have a PVT report, you can go to the separator flash data page and pick up one of the separator flash experiment, and it gives you a point to match to for your solution GOR, oil formation volume factor, and bubble point. Then if you have an adjusted differential liberation data, by the way, you can adjust this yourself. There are quite a few methods available in the literature that you can use to adjust your differential liberation data using one of these separator flash experiment data. Or you can build an equation of state model, ensure that you properly match it, then generate a black oil match table from it, which you can now use as a match data in your PVT section, right? So these are the options available when you're using black oil. Then if the objective requires you to use an equation of state model, you have tools such as PVTP that you can use, but, you always have to ensure that if you're using an EOS model, you tune the parameters of the model especially for the pseudo components, to ensure that the equation of state replicates your experiment, right? So this is a recommended workflow that we use. There are several different ways you can achieve a match for your fluid using an equation of state model, but we use, this is a recommended, you bring in the composition, check for mass balance, import your lab experiment. In the new PVTP, the latest version, what you'll find is that you can import an Excel file that contains your PVT experiment into PVTP. Then you can now use that file to as the database for tuning your whatever equation of state model you have picked, whether Penn-Robinson or SRK. And once you do that, you also have to ensure that your tuned model, is able to replicate your experimental data, your lab experiment. So once you achieve this, then you can now use that model to achieve other objectives. So like I mentioned at the beginning of this key consideration, your PVT modeling is critical to the success of any integrated asset modeling project. And we've seen a range of cases, from having very limited data, what option do you do, to having complete set of data, to having a PVT report that you can build an equation of state model. And from the equation of state model, you can generate a black oil table. These screens are from PVTP. So once you've tuned your EOS like this, and you are sure that, okay, yeah, it replicates the fluid behavior, then you can go to the export menu and export a black oil table if you plan to use that model, the black oil version of it. So when you export the table, then you can use it to match correlations, right? So which is the example that we have done here. So this model that we have tuned, right? We exported the black oil match table, brought it into Prosper, and used it to pick the appropriate black oil correlation. And in this case, you see that Lasata matches the solution GOR formation volume factor pretty well, and Petrovsky matches the viscosity very well here, right? So those are the options available for PVT modeling, based on your objectives and based on data availability. But ensure that you actually spend quite a bit of time, exhaustively on the PVT aspect of things. So once the PVT model is built, then in our hierarchy of workflow, we go into building the material balance models, right? So we go into building the material balance model. So as you can see, even from this structure here, PVT is the foundation, and we build the reservoir model. So with the reservoir model, we can now start, building the well performance models. Then the reservoir model, obviously, the reservoirs range from simple and straightforward structures to complex structures, to systems that, okay, you can't even build with material balance, is not adequate, right? So and what we want to achieve at the end of the day is we want to go from where we enter our raw data to where our raw data matches the model, the tuned EMBA model matches the production history, right? And what you need to ensure is that in terms of consideration, ensure that the production history is consistent with the PVT data. or the PVT model. So one of the ways that you do that is that if you are above the bubble point, as you can see on the bottom left corner, then your produced GOR should be the same as your solution GOR. That's pretty much the physics built into MBAL, or the assumption built into MBAL. So you build some MBAL models at times and you run simulation or forecast and it tells you, oh, the tank has run out of gas, right? It means that, oh, in above the bubble point, you're removing more gas than you have in the PVT model in solution. So ensuring that consistency, that when you're above the bubble point, RP is equal to RS, gives you that consistency between the MBAL model and your PVT model, right? Then you can also reference the whatever structural information you have in terms of building your model, right? Like in building the aquifer, for instance, we can get an estimate of, say, reservoir radius from the structural maps. So we can see if there is any major faulting, and we can build that into our aquifer models in terms of what range of encroachment angles can we start with, right? What range of reservoir, what value of reservoir radius can we use as an estimate? So, having some structural information or understanding on the one hand helps you with the achieving a useful material balance model at the end. And like I mentioned, it can be a simple tank like this where you just have an aquifer attached, or it can be a case where you have to actually link in several, a couple of reservoirs linked together if there is evidence of communication between the layers, right? So this screenshot here is actually showing two reservoirs that seem to be in communication through a common aquifer. And that model was actually captured here with an MBAL model. So if you don't have that understanding from the structure, then you struggle with a single MBAL reservoir for long, and you can achieve a suitable match. So a bit of the background on the structure is important as well. Then if you have other reservoir descriptions available, you can compare them with your material balance to ensure consistency, right? So there are cases where you have a numerical simulation model that is reliable, and we use it to run a forecast, extract the forecast result from the simulator, and use it as history in MBAL. And that way, MBAL prediction and the simulator prediction will be equivalent in terms of the prediction of rates and pressure drops and all that over time. So those are the kind of some considerations that you need to be aware of in modeling your material balance. Then we now move to the wells, right? In terms of the hierarchy, once you do the PVT modeling, you do the reservoir modeling, then you start building the well models, right? So you don't want a situation where you build your well models, match them to data, and by the time you run your forecasting gap, the IPR data being supplied by the MBAL model is start giving you different sets of rates from what you match the well to. So you have to ensure that when you are doing the well matching, the pressures in terms of the reservoir pressures that you use in your IPR for any point in time in the history of the well is the same as what you get from the material balance for that particular point in time, right? So that ensures that you are tying the well and the reservoir models together in a reliable manner, right? So typically, you have your completion report. We translate that into Prosper, ensure that there is consistency between the actual well and the model we have in Prosper. Then if you have flow ingredient survey data over time, then that's the best case scenario, meaning that you can use the flow ingredient survey data to select a multi-phase flow correlation, right? And with that multi-phase flow correlation, you can pretty much determine a PI or a skein value depending on the model that you are using, right? So with Prosper as well, we can also, analyze the entire well performance over history and determine the value of PI or skin value required to match the measured rates by the model at any point in the history. So that means that, if there are activities in the history of the well that resulted in a change in PI or skin, we can actually, see that in the well analysis. Then in a case where we don't have flowing gradient survey data and we choose a default correlation for the VLP calculations, Petroleum Expert 2 is a widely used default correlation in the absence of flowing gradient survey data. And Petroleum Expert 2 has been proven to perform very well within Prosper for a very wide range of cases. So that can be used as a starting point. Then you can carry out analysis like this, where you calculate the PI or skin required to get a match over the history of the well. Then what you can see in this screenshot up here is that in this case, the PI within the last 3 years or so hovered about around the value, right? That PI hover around the value, that shows that if we use this PI, the average of this PI for the model, then it's going to give us a very realistic performance of the well over time, right? Because these are probably like 50 well test data, and we are able to use an average PI to we're able to predict an average PI for all the well test data, right? So in the absence of this flowing gradient survey data with concurrent well tests, you can leverage on this kind of analysis to ensure that whatever skin value or PI that you're choosing to model the inflow performance of the well is based on realistic and solid analysis. So we also do this kind of analysis when we, because typically in a project, you have a range of conditions, right? You have some wells that have all the data set that you need, and you have some that have the barest minimum. Then you have to fill the gap between those two extremes. Then once you have reliable, robust well models, then you can go into gap where you bring the reservoir models, the well models, and you model the surface facilities, surface equipment within gap. Then within gap, you can now start carrying out the integrated asset analysis. So in terms of Prosper, before we leave, we have a poll that it's a multi-choice question. So we can just to check how much of these correlations that you are aware of. So a multi-choice poll. So select which of the correlations in the poll that you believe is cannot be used, that should never be used for modeling. So which of these correlations do you believe should never be used for multi-phase flow modeling within the well? So we're receiving your responses. We're receiving some responses. We have Hagedorn and Brown, gray correlation, leather flow, Fancher and Brown. Let's receive a few more responses. That which correlation here do you believe should never be used for modeling a well, or quantitatively modeling the performance of a well? So we can keep the questions in a few minutes. We'll round up, but we'll keep the questions till then. But you can type whatever questions you have in the chat. Let's get a few more responses to this poll. Yeah, we see that we have Hagedorn and Brown, gray, leather flow, and Fancher and Brown. Okay, so the Fancher and Brown correlation, exactly. The Fancher and Brown, okay, we'll get to that soon, Abdullahi. Thanks for your question. The Fancher and Brown correlation should never be used for modeling a well because it's a no-slip correlation. So for the people that have attended some of our IPM courses, you know that, okay, Fancher and Brown is there for quality check only because it doesn't make realistic assumptions. The other correlations here are actually quite widely used. Hagedorn and Brown. Gray correlation is useful for gases and condensates. Leather flow correlation is mostly for, it's a mechanistic correlation. What you find is that if you have Prosper, you need the additional licensing to use leather flow. So in Prosper, Petroleum Expert 2 is recommended as a default correlation if you don't have any flow ingredient survey data that you can use to select the appropriate correlation for your field. And it works very well for Nigerian fields as well. For most of the cases, 80–90% of the cases where we have flow ingredient survey data, Petroleum Expert 2 works very well for them. So the answer is Fancher and Brown. Thank you for the responses. So then we go into GAP, where we bring in the reservoir and the well models, and we now start carrying out the, we validate it with field data. So then we now start carrying out the analysis in terms of the deliverables that we can achieve, right? So like I mentioned, some of these deliverables are based on projects that we have implemented. Some of them, I think one of them is based on a project PETEX implemented. Then one of them is just a generic example, right? So like I said, in terms of the polls that we shared earlier, we see that production optimization is one of the most popular objectives that people said, yeah, you can achieve with an IAM. So we look at production optimization. So typically production surveillance, production optimization, forecasting production, and under production optimization alone, you have quite a few options that you can use to improve the performance of your assets, right? Choke size optimization, wear route optimization, the bottlenecking, and so on, right? So the objective, this is not an exhaustive list of deliverables you can achieve. There are a lot more you can achieve based on your own, whatever problem the field is trying to solve, or based on the objectives of the business itself. So the first deliverable we'll look at is production optimization, right? So let's start with choke setting optimizing choke setting, right? So we said production optimization, there's choke size, wear routing, lift gas allocation, pump performance, the bottlenecking, and so on. So if you start with choke setting optimization, what you're trying to do is you are telling GAP to advise you on what the optimum choke setting should be for the wells. So, and in order to guide GAP to set the choke setting within a limit that is not outside what you would consider safe operating limit for the well or the facility, you need to introduce some constraints, right? So the constraint can be at the surface. Maybe you cannot handle more than a certain total production at the separators, or at the well level. Oh, this well has this drawdown constraint. This well has this erosional velocity constraint. This well has this minimum production constraint, right? So the first thing we do when we are trying to carry out choke size optimization is to determine the operating limit of each well, right? And we use well operating envelopes like this, similar to this. We do well operating envelope like this, right? So what you're seeing here is for this particular oil well, the well test is the yellow you're seeing here. Then the point here is the minimum stable rate. So below that, this is determined from the VLP. Below that, the well is unstable. Then at the point here is the maximum rate that we can set for the well based on erosional velocities, drawdown constraints, minimum flowing wellhead pressure constraint. Then for each well, we can enter that limit that, okay, you cannot go outside this limit for this well. So we do that for oil wells. We also do that for gas wells, right? For gases, you have the VLP minimum. You also have the Turner criteria that we can build into the operating envelope. So we do this for all the wells in the field, then impute it as the constraint within which gap has to optimize, right? So it means that when gap is optimizing, it already has a guide. And the optimization in gap is such that it tries to minimize secondary phases, particularly water production. So it's going to produce more from low water producers and less from high water producers, right? So we set these constraints and generate this operating envelope for each well, set them as constraints in gap, also enter the surface gathering constraints before we now carry out the choke size optimization, so that when we carry out this optimization, we know it's within safe limits that the engineers would have advised, right? So we do that for oil, we do that for gas. So these slides are just showing how those limits are achieved. So this is like the minimum stable rate, for instance, that you get from the VLP, right? So if your well intersects within the minimum region, then it's likely to be unstable. So we want the well to intersect in the region where we have this positive slope for the VLP for it to produce in a stable manner. Then we have Turner criteria for gases, where the minimum velocity below which liquid starts dropping and accumulating within your well. Then we have tubing erosion based on SP RP14E and DNV erosional model that is within PROSPER. Then we also look at minimum wellhead pressures. We also look at maximum drawdown constraints. And with that, we generate these operating envelopes for gases and oil wells, right? Then those operating envelopes are now used as a guide in setting the limits for the choke size optimization. So then that's choke size optimization, and how to go around it to ensure that gap gives you ranges that are safe enough, right? Using the operating envelope of each well as a guide. Then there's well routing optimization that you can achieve as well, right? Depending on where a well is routed and depending on the pressure regime of the other wells, they can affect the production performance of a well. So you can get more from the field just by rerouting the wells, right? It's easy if the wells are very different pressure regimes, but it becomes difficult when there is a kind of range of pressure regimes for the wells. Then within IPM, there's a tool called gyro that you can use for this. You can also do this manually and solve the model for each one, iterate to see which one gives you the best performance over time. But you can easily do it as well using a tool called gyro in Resolve. Then if you route to a high pressure well or a low pressure well, the models can actually advise you on what you can get. Low pressure separator, the models can achieve you on what you can get. Then the models, let's say it's an ESP operated well, also advise on what speed you need to adjust the ESP to be able to flow to a certain separator. Then the bottlenecking is typically one objective that you try to achieve with IPM as well. Obviously, there are times that you solve a gap model and the bottlenecks are highlighted. So that's easy to identify. Then you now start thinking, okay, how much more can I get if I, resolve these bottlenecks? So just by, increasing the capacity of certain flow lines or pipelines within your system, you can reduce the back pressure on the wells flowing to that pipeline, and you can get more from the system. It can be as easy as that, or it can be a case where you have to look at each well, compare each flow line, compare measured pressure drop across the flow line with calculated, then you can determine if there are restrictions, maybe there's accumulation of wax, scales, or so within the flow line. Then the models can be used to determine that. Then once you have that, then you can determine if this flow line were free, then what will be the additional production I can get from it? So that kind of debottlenecking can be done within IPM, within an IAM. Then you can also use IAM. This is still, production optimization to determine how to optimally allocate gas to gas lifted wells, right? How do you optimally allocate gas to gas lifted wells? So you just give GAP the total amount of gas that you have, and you give it the range that it can send to each well. Then GAP uses that, to determine how much it needs to send to each well for the optimization, right? So this example, for instance, there is 10 million amount of gas available, and it's allocated a certain way, and they are getting about 3,800 barrels of oil. Then once it's GAP is given the allocation to do, GAP redistributes the lift gas available and gets about 1,000 barrels more of oil, right? Though this is just to highlight the feature, people have actually used this feature to allocate gas in a more efficient manner, right? So because you can think of allocating gas to well as a gas lift performance curve problem. Yes, it is, but the problem with that is that when you are gas lifting a well, the gas lift performance curve is based on what other wells in the network are producing to the network, right? Because it's based on the wellhead pressure of that well, and the back pressure from other wells can affect that. So that makes it a non-linear optimization problem. So imagine if you now have to combine that with choke setting optimization, then you need a tool like GAP to help you determine what the optimum setting should be. So these are just a few examples of some of the objectives that you can achieve with GAP. Obviously, achieving these objectives starts with building a reliable model in the first place. And we have discussed, the key considerations to look out for when you're building a model, and principal among this is the PVT modeling. And we showed all the options available for, developing a PVT model, all the way from limited black oil data to equation of state models, right? And the objectives you can now achieve with your gas lift data. So thank you very much for taking out the time to join us. We can keep the conversation going after this. You can always contact us, by email at info@acriteltd.com, or giving us a call. Then, like I mentioned at the beginning of the discussion, if you have IAM related problems or projects, we can definitely, we'll be happy to assist with that, either through a complete study or QC models, on-site support. And we have integrated production modeling trainings as well, right? So we can start handling the questions now. So you can either type in your question, or you can raise your hand and we can activate your mic so that you can ask the question directly. So before now, we had a few questions that were typed. I think someone typed it. If you have a question, please raise your hand. Then we'll activate your speaker, your mic. What is the minimum data requirement to carry out IEM in a brownfield? Okay, obviously, we talked about IEM earlier. This is a question from Abdullahi. And looking at this pyramid here, right? So we're talking about principal fluid property data. Then obviously, if it's a brown model, you have production history, and production and pressure history is critical for building an MBAR model, Then you need your completion report, your well test data, right? And data around your flow line length and elevations, to carry out this IAM. Each of these data I've mentioned, in terms of the level of availability, will vary from limited to extensive, right? And in the beginning, we covered how you can handle limited data when it comes to PVT, and how you can handle limited data when it comes to well modeling. So for PVT, for instance, we said, if you have limited data, it can be a case of looking at, you have just GOR, API, and specific gravity, and you can just, in that case, you have to fall back on what correlations perform best for the field you are dealing with or the region, right? Then if you have some basic lab data like bubble point pressure, GOR, and oil formation volume factor, then you can use that as a match data to tune the correlations, from which you can now select the correlation to model going forward. So in terms of the minimum data you need, I would say fundamentally important is PVT data in some form. Obviously, the production and pressure history of your reservoir, then the well completion report and well test data. That should suffice as the starting point, and you can now start tuning it to match the overall production data. Thank you for the question, Mr. Abdullahi. There is a question from Adejoke Adebayo. From your experience, is it possible for the flow correlation of the well to change over time, say from PE2 to PA3, for instance? Okay, and then there's a second question. Okay, yeah, well, to change over time, obviously it's possible for the physical conditions of the well to change over time, right? It's possible for the fluid flowing into the well to change over time. So what you can find happening is that it's possible that if it's an oil well, maybe there is scaling happening within the well, then all of a sudden the correlation you started with be it PE2 or PE3 is not matching anymore, right? So it shows that there's something happening physically within the well that the model is not able to capture. And that can be seen as an opportunity to actually understand better what's happening. So in that kind of situation, if you carry out a flowing gradient survey, then you can go back again and compare the correlations. But typically, if something is happening physically within the well, it's going to affect frictional pressure drop. And what you will find is that the majority of the pressure drop for an oil well is based on the weight of the fluid, right? And frictional pressure drop is minimal. So even if something is happening within the well in terms of scaling or deposition, then it has to be extensive for it to knock the correlation off significantly. So when you see that happening, then I guess it's an opportunity for you to actually, carry out some, surveillance work and to determine what exactly is happening physically within the well. But if there's nothing happening physically within the well, then your correlation shouldn't change ideally from one to the other. Obviously, for PE2, for instance, and PE3, they are the same correlation. PE3 is just used for, more like more difficult fluids, like foamy fluids, or with maybe higher gas fractions. So maybe if you start producing much higher GORs, then you might get to a situation where PE3 is looking like it's matching better than PE2, which is what is designed for. But this situation happening is an opportunity for you to carry out a surveillance to understand what's happening better. And if EOS has been used for the PVT, do we also have to select EOS for modeling, or can we choose black oil? It depends on the objective. If you have an EOS model for the fluid, this is another question from Aditya Care. So if you have an EOS model for the fluid, you've already built an EOS model, you've characterized the EOS, you have something like this, right? You've gone through the process where, you enter the composition, you did all this, and you're able to match and replicate the lab data. So if the objective is such that you need an equation of state model, maybe you're modeling a condensate or a volatile oil, or you're carrying out process calculations, then you can use the EOS model directly in Prosper. It means that under options, you have to choose EOS. But if you have equation of state model built for the fluid, but it's a black oil that you can actually just use a black oil model for, then you can select black oil and generate a match table from the EOS. Within PVTP, you can generate black oil match table. So once you export it, then you can bring it into Prosper as your match data, and you can now use that to select a correlation like this. In that case, you have an EOS model, you converted it to black oil, you generated a black oil match table from it, and use it to select the appropriate correlation. So it depends on the objective you're trying to achieve. That will determine whether you select PVT or EOS or black oil when you are now modeling the fluid. So I think we have a question. Somebody raised their hand. Saleh Babangida. Okay, you can go ahead with the question, Mr. Saleh. Okay, then afterwards we have Adejoke Adebayo. Unmute, you can unmute yourself and go ahead with the question.
Okay, thank you very much for the wonderful presentation. This is a welcome idea at this moment in time. We are looking forward to carrying out integrated asset modeling at the moment. And this is a very good window. I believe Isiaka has asked a question which is related to what I wanted to say earlier with respect to the data requirements. So my further question is with respect to that. If we're looking at the data matrix that will be required for this IEM to be carried out successfully, what would be the gap that can hinder one to carry out this study? That is the area I wanted to find out. So that if you don't have this particular data, you'll not be able to carry out integrated assets modeling. Thank you very much for the wonderful presentation.
Okay, thank you. Thank you for the question. Yeah, so going back again to this pyramid that we have here, that is pretty much showing the hierarchy or the workflow, and the workflow here is also pretty much set up in the order of importance in terms of, roughly anyway, in the order of importance in terms of how the data that is needed and how the models should be built. So the starting point can be, like I explained at the beginning, can be, okay, look at the objectives. What objectives are we trying to achieve? Then look at the components of the production system and the fluid types. So once we review the objectives, the fluid types and the components, and also the models, the technology that we need to build those models, then we can now move to the point when we start the modeling, right, where we look at the fluid property data. Like I said, in terms of data availability, whenever we're building a model, whenever we have an IAM project, we deal with the entire spectrum of data availability, right? From where very limited information is available, all the way to where we have multiple redundancies that a particular well or reservoir has a particular set of data, and multiple that we now have to determine, okay, which of these should we use, right? Well, like I said, we deal with these extremes, and in each case, we now have to look at, okay, what's your understanding of the team in terms of the, with respect to the data available and the objective objective we're trying to achieve and the model we're trying to use to achieve that. So it's typically on a case-by-case basis that we'll be able to determine, okay, do we have enough data to continue? Because for PVT modeling, for instance, you can have a case where you have a PVT report, which is the ideal case you want to be in. Or you have a case where all you have available is over time, the GOR measured at the field, the API estimate of the fluid, and the gas gravity. Then, even with that, we can still build the PVT model, right? Because if you have GOR over time, we can trend it and say, oh yeah, over this period, the last 1 year, 2 years or so, this has been the average GOR. So we can safely say, okay, this can be our GOR input into a black oil correlation. We have the API of the fluid and we have the gravity. Then we can go back and say, okay, for this field, is there any other nearby reservoir where there's a PVT report? Okay, for these reservoirs, what correlations work best for them? And if the fluids are similar enough, then we can safely use that correlation to build the PVT model till more data becomes available, right? Then we move to the reservoir model. So for the M-bound modeling, there is production history. We also work with a range of cases where there's probably just initial reservoir pressure available all the way to where you have almost every year or so kind of BHP data available. Then on a case-by-case basis, we try to build the model. Obviously, the level of confidence you would have with limited data is different from the level of confidence you have when you have the complete set of data. So in each case, when we are building the model, we are creating a range, a window of uncertainty and say, okay, yeah, based on our understanding of the models we are using and the correlations we're using, we know that we are within 10% of what the likely answer should be, or we are within 15%. So we build that window of uncertainty around the models based on data availability. But I would say that, in almost every case we've come across, we've been able to at least develop a usable model that can, later now be updated as more data becomes available. Yeah, but we can also take the discussion further and, maybe you can send us an email after this, or we'll contact you if we can get your contact from here. And we can see how we can support you with your modeling effort. Thank you. Then we have Adejoke Adebayo. Okay, so you can unmute now and ask the question.
Good morning. Good afternoon. Hope you can hear me.
Yes, I can. Good afternoon.
All right. Thank you very much for the discussion. I mean, it was very helpful. So the question I have is in two parts. Number one is, are you going to organize a session to resolve anything soon? Interested in that. Then secondly, I was building an integrated model. And my question is it possible to couple a dynamic simulation for the reservoir model in GAP? Because the Ember we're using had like bits of limitation. So I tried to see if there's an option outside using Ember. I saw something, but the input required for that was really limited. It might not have really represented in terms of the entire process. I'm just wondering, for GAP, must it be Ember? Can we import simulation? Or does it have to be written?
Okay, thank you for the question. The line was breaking a bit, but what I could get is that you asked if we have a session on resolve, right? And you also asked if it's possible to couple a dynamic simulation in GAP, right? So is that correct?
Yes, yes.
Okay, okay. All right. So we have training sessions on Resolve, right? We have training on sessions on Resolve regular. You know, I think like once a year or so, we try to organize a training on Resolve. And PETEX as well also have 1 or 2 sessions on Resolve yearly. So, but in terms of the webinar on Resolve, we're not planning anyone anytime soon, but we can have a chat with you outside of this to see what you're trying to do and what options are available for you to achieve your objectives, right? So you can just send us an email after this and we can take it from there. But in terms of coupling dynamic simulations with GAP, yes, it's possible, but it has to be through Resolve, right? So, you have to build the GAP model with the Prosper model, then bring the GAP model into Resolve, then integrate the GAP model integrate the GAP model with Resolve, right? So integrate the GAP model with the numerical simulator. So Resolve now handles the transfer of data between the simulator and GAP, right? So there are a few settings that you might need to make in your simulator to be able to use it in GAP, but to be able to use it with GAP in Resolve, but they are quite straightforward and they can easily be implemented. So if it's a case where you need to, you already have Resolve and you have GAP and you have the simulator, there are 2 options available. You can go into Resolve and set it up in Resolve and run it coupled with Resolve, or you can, like I mentioned at some point, run run a prediction with the simulator, extract the results, and use it as history in MBAL. Then that tunes the MBAL model to the results that the simulator is already predicting. So what you'll find in many cases is that the production, pressure prediction, water evolution, and all that MBAL would predict to be quite similar to what the prediction of the simulator is. So there are 2 ways of going about it. Either that or you link it directly with GAP using Resolve. But like I said, we can send us an email later, or give us a call and we can take the discussion further. Yeah, thank you. We have Stanley. So Stanley, you can unmute now and ask the question.
Yeah. Good afternoon, Lukman, and good afternoon, everyone. Thank you very much for this. Can you hear me, please?
Okay, I think you might need to speak up a bit, or maybe change the.
Good afternoon,
device.
Lukman.
Okay, yeah, I can hear you.
Everyone. All right. Thank you very much for this presentation. I actually picked interest, one of your slides where you have operating envelope. If you don't mind, you can go back to it.
Okay.
Okay,
Did this slide?
fine. Yeah. Okay, yeah. Let me first ask, these plots, I actually do this operating envelope, right? More like from Prosper. I don't know this plot, but it doesn't seem to appear in this form, right? It's just the VLP IPR where I have I've already been able to establish my cutoff rate, more like critical rate I shouldn't go beyond. And as well as the optimum as well. The minimum rate that is it to credit, right? Then with that intersection of VLP IPR, I'm able to more like with the choke size come up with this operating envelope, but it doesn't seem to appear in this form, right? So I was going to ask, is this generated via Prosper, or are there other tools that you use to generate this?
Okay, yeah, thank you. Yeah, so we generate this with Prosper, and but it's pretty much a plot of flowing wellhead pressure versus liquid rate, right? So what we do is once the Prosper model is calibrated, then we generate this plot, the black one, and what you see as the black one is the flowing wellhead pressure versus rate of each one. So what we use is, because of to be able to achieve this in unstable region, we actually use open server with Prosper. Then we extract the result into Excel and plot it this way, right? So all these calculations, minimum stable rate, for instance, comes in from the VLP IPR calculation that you mentioned. Then at each rate, we also calculate the erosional, the maximum erosional velocity, the C factors. Then we carry out is a combination of several different calculations. In this case, it's pretty much a gradient calculation at different rates to get the different wellhead pressures for the different rates to get its principal curve. Then we do a series of VLP IPL calculations, and from those VLP IPL calculations, we get minimum stable rate from the VLP curve. Then we do one for the minimum wellhead pressure and see what rate it gives us. Then we do the erosional velocity calculations for different rates as well and plot it on the plot. So it's a combination of Prosper, Open Server, and Excel.
Oh,
yeah.
Okay, that's fine. Thank you very much.
All right, thank you. Okay, so do we have any other question from anyone? So on the chat box, there is our number is there, the office number and email, info@acriteltd.com. You can always contact us there. If you have any general question to ask, or if it's IPM specific question, you can contact us at ipmsupport@acriteltd.com. I've typed it in the chat box as well. So we'll be happy to hear from you, and also be happy to support you with any IPM or IAM related issues you might have. We're partners to PETEX in Nigeria. So if your IPM software is maintained, then the technical support is free, right? So it means you can contact us, and whatever issues that you might have, we can be the first line of support, and we can also get PETEX involved as well if the issues are beyond what we can handle locally. So feel free to get in touch with us. Even if you don't have the software, you can get in touch with us, and we can, also give you all the options available for acquiring the software. And if you have, integrated asset modeling projects being planned, you can also talk to us. If you have an existing IPM model and you want it to be quality checked and to achieve objectives, you can get across to us as well. So thank you very much for taking all the time to join us. We appreciate it. So we'll send a copy of the slides across to all the participants, and we hope to have you again sometime soon on one of our webinars. Yeah, thank you.